All right, so these are kind of some photosynthesis extras, I guess. And so there's two concepts here. The first is photorespiration. And I have to laugh because I've taught this for many years. And so I'm going to say this and it sounds stupid, but I want you to know that photorespiration is bad. It's bad. It's bad. It's not good. It's bad. Now, I'm trying to make a big deal about this. For some reason, students don't necessarily get that. Okay, so photorespiration, what I haven't really shown you yet and what you'll get more of is we're going to talk about cellular respiration in our next sets of videos. And that's where you're basically taking oxygen or you're breaking down sugars basically to make ATP. And so it's really the photosynthesis equation in reverse, I guess, is how you could frame that. So as a plant, you don't want to do that. Plants do need oxygen, don't get me wrong. They do pull oxygen in through the roots and they need to use some, but their cells are not burning as much energy as we are. And so overall, they don't need that much. Or at least not as much as we do. Okay, so with that in mind, when a plant is going through photorespiration, it basically shuts down its sugar production and goes in reverse. It actually burns its sugar, and it does not want to be doing that. So if you're a plant, you're not growing, you're not making sugars. And so you ask, why do we teach this? In reality, we should be teaching it, especially here in Southern California. And Campbell, the Campbell book was authored by or at least used to be authored by Campbell. He was a teacher at UCR. And unfortunately, he passed away a few years ago. But it's been taken over by some of his colleagues who were helping him write and then taken over. He actually had just retired from writing when he passed away. All right, so what I need you to know is it happens on hot, dry, sunny days, which we don't have any here in Southern California. And actually, I'm being sarcastic because that's kind of all we have is hot, dry, sunny days. So what happens is plants have to have evolutionary wise figured out how to get around this. And so there's some evolution techniques that have happened in plants that allow them to kind of get around this process. Okay, so here's what I want you to know, and this is maybe a little bit difficult for people, but most plants are what we're going to call C3 plants. And it's because of the 3-carbon sugar we talked about, the G3P. Okay, so that's where the 3-carbon, okay, so called C3 plants, most plants. But there's been 2 evolutionary changes that have come around, and we have names for those, and that is called the C4 plant and the CAM plant. And C4 plants are going to make a organic acid different. They're going to make actually what's called maltate, and so, which is a 4-carbon sugar. That's where that name comes from. And CAM is named after it's a process named after a family of plants, succulents, that do it that way, in cactus, things like that. So here's what I want you to know. These are not, what we're finding out now is they're not independent of each other. Actually, plants can do actually both. It turns out there are some plants that can do C4 and CAM depending. So we're finding out these processes are not exactly as cut and dry as we teach them. But we're going to do that for you just to make things life a little bit easier. Okay, so what I've done on the next page is I've put up the next slide, I've put up a picture here kind of comparing what happens. So in a normal plant, that's the C3 plants, photorespiration typically on a hot, dry, sunny day is high. In C4 and CAM, that's low. Okay, the enzyme that we showed you in the Calvin cycle was called rubisco. That was the one that captured CO2 in C3 plants. C4 plants and CAM plants actually use a different molecule, and that's called PEP carboxylase. PEP carboxylase. So again, that's another CO2 acceptor. It's a different enzyme and a different protein, and it works better, a heck of a lot better. Matter of fact, Rubisco is probably the most common protein on the planet because it's in most plants, almost all plants. But Rubisco is not really all that efficient. It turns out if there's low levels of CO2, it starts grabbing oxygen, and that will eventually shut the plant down and make it start burning its own sugars. Very similar to hemoglobin in us. Hemoglobin picks up oxygen. Unfortunately, hemoglobin also picks up carbon monoxide. And when carbon monoxide is available, that seems to be what it likes better, and that'll actually kill us. So kind of similar process. All right, so for the sugars it makes, the C3 again comes from the PGA. I think I called it G3P in the slide before. That was wrong. It's the PGA. And then C4 actually is using malate, which will then go into what's OAA you haven't seen yet, which is oxaloacetate, both in C4 and CAM plants. Okay. Okay, so and then location. Remember we told you that C3 plants, mesophyll, that's where most photosynthesis takes place. What you need to know is in C4 plants, it shuffles it all into what's called the bundle sheath cells. And these are cells that are surrounding the vein. And then in CAM plants, the Calvin cycle still happens in the mesophyll. The stoma or stomata in normal plants are typically open during the day and closed at night. Same for C4 plants. And then CAM plants, it does it differently. It closes at night and closes in the day and opens at night, which is reverse, because in CAM plants, those are usually desert plants, and one of their biggest concerns is water loss. So another big factor. So examples of C3 plants, or most plants do that. C4 plants would be sugarcane, corn, and grass. And then CAM would be pineapple, cacti, and succulents. Okay. So here's a C4 plant. And I wanted to kind of just explain what's happening here. So you can see we mentioned the oxaloacetate. You can see the word there, the 4-carbon sugar, but maltate's the one that actually pushes across. But the name actually comes from the OAA. But here's what you need. Here's what you need to understand. What's happening here to make this a little bit different is I only have so much CO2. So what I'm going to do is, instead of trying to do the Calvin cycle all throughout the plant, I'm going to actually kind of just overpump my CO2 into the bundle sheath cells. And to do that, that way I'm sure that those the Calvin cycles will actually produce a lot of sugar. So I'm not going to do the Calvin cycle necessarily in the mesophyll cells, because that would be a waste, and that's where I'm going to have my photorespiration. So I have my specialized cells here doing it, and it makes sense. I've got an older home, and it's hard for me to explain this. Maybe on video I could do it better, but it's funny because built in 1911, this was before they had central heating, and so I have a dining room next to my kitchen, and there used to be a door there, and you can see the place in the wood where the hinges were, and eventually that door's been gone, and I'd like to replace it. And then there's also I have what's called pocket doors that go between my dining room and my living room, and again, those are also missing, been taken out years ago, and I would like to replace those. But the question is, why in 1911 did they have these doors? And you could argue, well, if you have people over, you don't want them to see the kitchen, and that is probably that at least used to be true. I mean, now we have everybody in the kitchen. But more importantly, I had a potbelly stove in the dining room, and the idea behind that was you would heat the one room, and so all the heat, you could close those doors and keep the heat in that one room. And so this is the same thing, is you're going to put all the CO2 into your bundle sheath cells, so you maximize your ability to make sugars. Now, the CAM process, on the other hand, and I don't really have a good picture from this, I kept looking for one, but the idea here is that during the day or at night, I'm making all these sugars, this OAA. I'm doing my process. The Calvin cycle is at night. But what I'm doing is during the day, I close my stomata, so I don't have access to the oxygen and the CO2. So what happens is during the day, I'm making my ATP and my NADPH, and I'm just storing it up. And then at night, when my stomata are open, the CO2 comes in, I can now do my Calvin cycle with my stored energy. So I'm kind of flipping what I'm doing. It's all happening in the mesophyll cells. I'm just, because I have to close my stomata because of temps and water loss, I'm getting away with it. So these are evolutionary workarounds for a system that was not working very well. Okay, and then the last topic, real quick, talk about this more, and maybe we will some ecology, but the greenhouse effect. So here's a greenhouse. You can see a little tiny terrarium, and I want you to realize usually it's hot and humid in here because light can get through the glass, hits in here, and then the problem is that the heat can't get out and the moisture can't get out. So light goes in, but the heat gets trapped and the light gets trapped. And so that happens on this planet. We call it the greenhouse effect. Without this effect, we'd be dead. It'd be way too cold on this planet. We don't have glass surrounding the planet. What we have is a layer of greenhouse gases, mostly CO2. But what we're doing now is we're releasing large amounts of CO2 into the air, and we have what's called global warming. And now we're talking about what we're talking about is climate change. And what I want you to realize is what climate change actually is yes, the planet is warming. Yes, that is not good. And I want to make sure you understand what we're talking about. What's happening is we are getting a thicker and thicker layer of CO2, which is causing more temperature to be trapped in, and it is causing a warming of the planet. And that warming is not hugely big. We're talking the estimate is only a couple of degrees Celsius. We're not talking 10 to 20 degrees Celsius. We're talking 2 to 3 degrees Celsius. And you're thinking, well, who the hell cares? Well, you should care, because the problem is what you have to understand. Global warming is probably not a great term. It is climate change. And what's happening is it's not just the average temperature is getting hotter, but we're seeing bigger fluctuations, which is what the red is showing. And so climate change means that we're having hotter and hotter areas and colder areas. We're talking about temperature variation. And for the plants and animals on this planet, that is not good. And it's because of evolving to this. We've had global warming in the past, and we've had ice ages in the past. And that's what people point at and say, oh, it's just typical. It is not typical. This is the first time ever it's happened this quickly. In the past, it has happened. Our planet goes through these fluctuations, but they've always been slow term, which gives plants and animals a chance to adapt. What we're seeing now is there is very little time for organisms to adapt. Many of these organisms have already been pushed by humans to an extent where they're barely surviving as is. So we're expecting massive extinction rates. And so, yes, it should matter. Will the planet disappear? No. Will life on this planet disappear? No. But it is going to make a huge difference. So how is it going to affect humans? Well, 2 to 3 degrees actually means that semi-arid areas are going to become arid. Just to let you know, you live in a semi-arid area, so this is going to become drier and drier. We're seeing that maybe now with all these droughts. We're going to see increased weather patterns, flooding. The Antarctic and Arctic ice is melting. It's not going to be Water World, the very bad Kevin Costner movie, if you know what that one was, but there's not enough ice to cover all the land masses in the world. but sea levels will rise. And so we're talking about flooding on the coasts, goodbye New Orleans, Florida. You know, you're thinking, oh, well, that's how we solve our retirement issues with all the old people in Florida. You know, I bought beachfront property in California. I live in San Dimas. You know, yeah, global warming. I'm just sitting on my porch waiting for the water to come up. But parts of Southern California can and or will be underwater. And so those are the things we need to worry about. Also that where we grow our crops, and much of our crops are grown in what we call the grain belt across the middle of the United States. We're seeing weather patterns change. The jet stream is actually shifting up north, which means that it's going to be harder and harder to grow crops across the United States. So make friends with a Canadian. That may be the next global bread basket. So it does have a major consequences for us. So I'll just end that with you're all going to die. So that'll end the share, and we're going to end the recording.